this episode, we take a close look at what separates automation that merely runs from automation that behaves responsibly when things go wrong. Most new learners picture automation as a smooth conveyor belt that either succeeds or fails, but real operational systems fail in partial, messy ways that can ripple outward if you are not prepared. Failure handling is the set of decisions an automated workflow makes when a step does not complete as expected. An automated rollback is the system's ability to return to a known good state without a panicked scramble. The phrase blast radius is important because it describes how far the damage spreads when a change is bad, incomplete, or misunderstood. When you design pipelines and deployments, you are not only designing the happy path, you are designing how harm is contained when reality is less cooperative. If you learn to think about failures as predictable events rather than surprises, you will build workflows that protect users, protect data, and protect the team's ability to recover quickly. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful way to start is to redefine what failure means in an automated delivery context, because failure is rarely a single moment. A job can fail because it cannot reach a dependency, because a configuration value is malformed, because a security control denies access, or because the application itself is unhealthy after it starts. Some failures are hard failures, where nothing was changed, and others are partial failures, where some changes were applied and others were not. Partial failures are the dangerous ones, because they leave systems in a mixed state that confuses both people and automation. Operators treat mixed states as high risk because the environment no longer matches the baseline assumptions that tests and procedures were built around. Good failure handling begins by detecting which type of failure occurred and choosing an action that is safe for that type. That is why careless retry loops can be harmful, because they can compound partial changes rather than restoring stability. When you can name the kind of failure you have, you can contain it instead of amplifying it. Before you can roll back anything safely, you need a concept of what safe means, and that requires a definition of desired state. Desired state is the version of the system you want to be true, including which artifact is deployed, what configuration is applied, and which dependencies are expected. If you do not define desired state clearly, rollback becomes guesswork because you are not sure what you are returning to. A rollback is not a magical undo button. It is a controlled move to a previously validated state that you can identify and redeploy. That is why versioning and immutability matter so much in rollback design, even when you are not focusing on artifacts directly. When a deployment fails, you want to revert to a release that is known to be stable, not to a label that might have changed. Operators also remember that desired state includes external assumptions, like database schema compatibility and feature flags, because rolling back code while leaving incompatible data changes in place can create new failures. Safe rollback is therefore a system design problem, not just a pipeline feature. Failure handling starts with detection, and detection must be grounded in signals that reflect real user impact rather than only job completion. A pipeline can succeed at copying files and restarting services while the application is still unhealthy, unable to serve requests, or failing to connect to required dependencies. That is why health signals and readiness checks matter, because they provide evidence about the system's actual behavior after the change. For beginners, it helps to think of this like checking whether a car engine stays running after you start it, not just whether the key turned. If your detection is too shallow, you will declare success while users experience failure, and rollback will not trigger when it should. If detection is too fragile, you will roll back too often for harmless noise, which creates instability and erodes trust in automation. Operators design detection to be meaningful, stable, and aligned with real paths that matter, such as the ability to respond to basic requests, connect to key dependencies, and maintain acceptable error rates. When detection is accurate, failure handling becomes calmer because the decision to act is based on evidence. Once you can detect failure, the next question is how to categorize it so the workflow responds appropriately rather than applying one blunt reaction to every situation. Some failures are transient, like brief network glitches or temporary service overload. where a controlled retry might succeed without risk. Other failures are deterministic, like a bad configuration syntax or a missing permission, where retries only waste time and create noise. An operator mindset avoids defaulting to endless retries because endless retries can overload systems, lock accounts, and turn a small issue into a larger incident. Instead, responsible failure handling uses bounded retries, clear stop conditions, and a plan for what happens after the stop. That plan might be to halt and alert, to roll back immediately, or to quarantine the change by preventing further promotion. Categorization also helps with communication, because saying the failure is a validation error is different from saying the failure is a dependency outage. When your workflow encodes this distinction, it reduces confusion during response because the system's behavior matches the nature of the problem. Automated rollback is most effective when it is designed as a normal branch of workflow logic rather than as a rare emergency script. When rollback is an afterthought, it often relies on fragile assumptions, like the ability to restore state from memory or the existence of a previous artifact that was never properly preserved. When rollback is a first-class pathway, it is tested, audited, and treated as part of the system's operational contract. That mindset also changes how you design your deployment steps, because you begin to ask whether each change can be undone safely. Some changes are inherently reversible, like switching a deployed artifact version, while others require more care, like database migrations or irreversible data transformations. Operators respond by separating reversible changes from irreversible changes and by adding extra safeguards around the irreversible ones, such as phased rollouts and strong pre-deployment validation. For beginners, the key idea is that rollback is not always about undoing every change. It is about restoring service stability and reducing user impact. Stability is the goal, and rollback is one tool to achieve it. Reducing blast radius begins with limiting where a change is applied before you know it is safe, because the best rollback is the one you never have to run at full scale. This is why staged deployment patterns matter, even if you are not yet deep into deployment strategies. When a change is introduced gradually, you can observe its impact on a small portion of traffic or a small set of systems before expanding. If the change is bad, you contain it to that smaller scope, and rollback affects fewer users and fewer components. Even in a simple mental model, you can understand this as testing a new recipe on one plate before serving it to the entire room. Operators use blast radius thinking in the workflow itself by combining validation gates, dependency checks, and eligibility rules that prevent high-impact steps from running until evidence suggests it is safe. This is also why environment boundaries exist, because you want mistakes to be caught earlier in less critical places with less exposure. When your workflow is designed to constrain scope, failure handling becomes more manageable because the consequences are already limited. Rollback also depends on what you are rolling back to, and that is where keeping known good states becomes operationally essential. A known good state is not just the previous version. It is a version that has been validated in conditions similar to the current environment. If the last release was also unstable, rolling back to it will not help, and your automation may bounce between bad states. Operators therefore track which releases were truly stable and treat those as safe anchors. They also avoid confusing stability with recency, because the newest stable version is not always the most recent build, especially during periods of change. This is where careful promotion practices help, because promotion implies a release has passed checks and is eligible to be considered known good. When you store artifacts immutably and track approvals and test outcomes, rollback can be a simple selection of a safe anchor and a redeploy of that anchor. For beginners, the important point is that rollback needs a destination that is both identifiable and trustworthy, not merely older. There is also a difference between rollback as a deployment action and rollback as a data action, and beginners need to understand that these two do not always move together safely. Code can be rolled back quickly, but data changes can be harder because data might be transformed, migrated, or written in a newer format that older code cannot interpret. Operators manage this risk by designing backward compatibility wherever possible, meaning new code can work with old data and old code can tolerate new data for a limited time. They also use feature flags and controlled toggles to separate deployment from activation, so a change can be deployed but kept inactive until it proves safe. This approach reduces blast radius because it gives you an additional lever besides full rollback, allowing you to disable a risky feature without redeploying everything. It also makes rollback safer because you can avoid coupling it to irreversible data operations. The goal is not to complicate the system, but to reduce the number of situations where rollback is impossible or dangerous. When you separate concerns thoughtfully, recovery becomes more reliable. Failure handling also includes what happens after rollback, because returning to a stable version does not automatically explain why the failure happened. Operators treat rollback as a service restoration step, not as the end of investigation. A well-designed workflow captures enough context to support diagnosis, such as which step failed, what signals triggered rollback, and what environment conditions were present. This is important because repeated rollbacks without learning lead to thrash, where the team keeps trying changes and the system keeps rejecting them, wasting time and eroding confidence. Good automation helps by producing clear failure summaries and preserving key evidence so humans can analyze without reconstructing everything from scratch. It also helps by preventing immediate reattempts of the same failing change unless something meaningful has changed, such as a dependency recovering or a corrected configuration being introduced. For beginners, this is a maturity lesson. Recovery and learning are different phases, and both must be supported. Recovery protects users now, and learning protects users later. Another critical part of reducing blast radius is designing safe stop conditions, because sometimes the correct response is not rollback, but halt. If a workflow detects that a prerequisite is missing, that credentials are invalid, or that the environment is in an unknown state, proceeding can create additional damage. In those situations, stopping is a protective action because it prevents the automation from pushing further into unsafe territory. Operators sometimes call this failing closed, meaning the system chooses safety over progress when uncertainty is high. This can feel counterintuitive to beginners who equate automation with always pushing forward, but safe automation knows when to pause. A rollback can also be unsafe if the system cannot confirm what version is currently running or if the rollback target is unknown. In that case, a halt with clear alerts can be the least risky choice. The key is that failure handling is not a single behavior. It is a set of responses chosen based on the type of failure and the confidence level of the system's knowledge. When you design for safe stops, you reduce the chance of runaway automation. Automated rollbacks should also be designed to be observable, because a rollback that happens silently can create confusion and can hide deeper reliability issues. If a deployment rolls back automatically, people need to know it happened, what triggered it, and what state the system ended up in. Observability also supports auditing, because rollbacks are significant operational events that affect system state and user experience. Operators value clear signals like rollback initiated, rollback completed, and rollback verification passed, because these signals allow the team to correlate user reports with system actions. Observability also helps you distinguish between a single bad change and a systemic problem, because repeated rollbacks might indicate a deeper dependency issue or an environmental drift that is causing many releases to fail. For beginners, the important point is that automatic does not mean invisible, and invisible automation is often dangerous. When rollback behavior is visible and well explained, it becomes part of the system's reliability story rather than a hidden surprise. It is also important to avoid common beginner misconceptions about rollback, because these misconceptions lead to risky designs. One misconception is that rollback always restores everything to the way it was, which is not true when data has changed or when external dependencies have shifted. Another misconception is that rollback means the pipeline failed, when in fact rollback can be a sign the system is healthy enough to protect itself. A third misconception is that you should roll back on any error, when sometimes a controlled retry or a temporary halt is safer than a full rollback. Operators choose rollback when it is the safest path to restoring service, not because it is dramatic or because it feels like a reset. They also avoid designing rollbacks that rely on fragile assumptions, like the continued availability of an old dependency version that has been removed. Instead, they design rollbacks around preserved artifacts, stable configuration baselines, and compatibility expectations. When you think about rollback as a controlled redeploy to a known good state, rather than as a magical undo, your designs become more realistic and safer. As these ideas connect, you can see that reducing blast radius is a layered strategy rather than a single feature. You reduce blast radius by limiting scope of change, by validating meaningful health signals, by categorizing failures correctly, and by using safe stop conditions when the system lacks confidence. You reduce blast radius by keeping known good anchors available, by ensuring artifacts are immutable and identifiable, and by designing compatibility so rollback is feasible. You reduce blast radius by making rollback visible and auditable, and by preserving evidence so the team can learn rather than thrash. Each of these layers makes the other stronger, because a rollback trigger is only useful if it is based on reliable detection, and rollback itself is only useful if it has a trustworthy destination. This is why mature automation feels calm during failure. It does not improvise. It follows an intentional design that was built with failure in mind. For a beginner, the main lesson is that resilience is planned, not wished into existence. To close, remember that automation is not only about delivering change faster, but about delivering change with control, especially when things go wrong. Failure handling gives your workflows the ability to react safely to different classes of problems, rather than treating every error as identical. Automated rollback gives you a fast path back to stability, but only when it is built on clear desired state, immutable artifacts, meaningful health signals, and compatibility-aware design. Reducing blast radius is the guiding principle that keeps both failure handling and rollback focused on protecting users and containing harm, rather than on proving the pipeline is clever. When you design workflows that can stop safely, retry responsibly, and roll back to known good anchors with clear visibility, you are building operational maturity into your automation. That maturity shows up as fewer prolonged incidents, less frantic manual work, and more confidence that the system will protect itself when a change is risky. If you can explain why rollback is a controlled redeploy and why failure handling must be evidence-driven, you are thinking like an operator who understands both speed and safety.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.